Welcome. This is the first in our equilibrium video for the equilibrium flip unit. Again, this is covering lots of chapters. So this is video number 1, in which we'll be covering what is K, what does it mean, what is the meaning of this value K, which we're going to be seeing throughout the unit, and also how to write an equilibrium expression. That's definitely going to be our primary focus. What is equilibrium? Well, as you saw, hopefully with the penny demonstration, equilibrium is when a state when the rate of the forward reaction is equal to the rate of the reverse reaction. And at that point, the concentrations of the products and reactants are going to remain constant. They are no longer going to change if the rate of the forward reaction is equal to the rate of the reverse reaction. Primary topics of equilibrium. As we went over in class, there's definitely an outline to this particular unit. So this video is on writing equilibrium expressions. That is the first of our primary topics, and along with that we'll be talking about what K means. The equilibrium expression and the equilibrium constant. So the way that we write this thing called the equilibrium constant, which is sometimes referred to as the law of mass action, so you saw that language in the POGL. If we have a reaction, AA plus BB goes to PP plus QQ, these are coefficients, and then the uppercase letters are actual chemical species. The equilibrium expression is written as this: Kc is equal to the concentration of the products raised to their coefficients divided by the concentration of the reactants multiplied together raised to their coefficients. That's what this thing is saying. Products over reactants raised to their coefficients and multiplied together. Kc is what is called the equilibrium constant. So this is a number, and that number is called the equilibrium constant. The entire thing, this whole thing, all of it, including the equals Kc, not just the stuff to the right of the equal sign, is called the equilibrium expression. If I ask for the equilibrium expression, I want you to write out this. You don't need the number for K, you need K equals products over reactants raised to their coefficients. The C, sorry, to go back, the C that's shown right here stands for concentration because those square brackets are indicating molarity. Kc does not use initial concentrations, but it uses equilibrium concentrations, so that's critical. You can't plug in initial concentrations and get a K value. K values have no units. There are no units to this. It is a ratio. And what does K mean? It has to do with this ratio. So because K has no units, you have to understand that it's simply a description. It's a ratio of products to reactants at equilibrium. It is describing what the system looks like when it's reached this state of equilibrium. Are there more products when we reach the forward rate being equal to the reverse rate, or are there more reactants when we reach the forward rate being equal to the reverse rate? That's what it means. That's what K is saying. It's a statement about the system at equilibrium. What do you have more of, reactants or products? So it's a ratio. How does K describe the system? It's based on this ratio. So the larger the K value, the more products you're going to have at equilibrium, because your numerator, because it's products divided by reactants, is going to be larger. The larger your numerator, the larger your overall value becomes. If K is significantly greater than 1, then we say that products dominate at equilibrium, and you basically have way, way, way more products than you do reactants. And we use the terminology that the equilibrium lies to the right, or that it favors the right. Products are always written on the right-hand side. Even if you consider a reverse reaction, the stuff that's on the right-hand side of the arrow, that's always the products, regardless of the direction you're going. You always say reactants are on the left, products are on the right. If your K value is smaller, then that means that you have more reactants at equilibrium because you're going to have a larger denominator. Again, it's products divided by reactants. So if your denominator is bigger, like if you say 1 over 4 versus 1 over 10, you get a smaller number, right? 1/10 is a smaller value than 1/4. So if K is significantly less than 1, then we say that reactants dominate at equilibrium, this state when rates are equal, and that equilibrium lies to the left, or equilibrium favors the left. Regardless of which direction you're going, reactants are always written on the left. What does Kc depend on? Well, basically, what influences Kc? Stoichiometry influences Kc because coefficients are involved. So if you change your coefficients, you will be altering your K value. Likewise, temperature. Different temperatures have different K values. Now, this is precisely like the kinetics rate constant, because the kinetics rate constant is actually very much related to K, as you also saw in the POGL. So you're going to be given temperatures in a lot of equilibrium problems. You're usually not using them in any sort of calculation, but like with kinetics, it's telling you at this temperature, this is this K value. And we're actually going to return to this later on and see how changing temperature influences the K value in a very predictable manner, and how we can actually predict how K will change for different reactions based on how you change its temperature. What does Kc not depend on in the slightest, meaning what is absolutely not at all related to the value of Kc? Reaction mechanism or kinetics. Kc is not at all dependent on how fast or how slow your reaction is, and that's a huge, huge thing to understand. Equilibrium does not care how long it took to get to equilibrium. No, no, no. It could have taken 2 seconds to get to equilibrium. It could have taken 2,000 years to get to equilibrium. But Kc doesn't care. It's just like, at equilibrium, what does this system look like? So you have to understand that a slow reaction says absolutely nothing about the magnitude of K. Absolutely nothing whatsoever. There is absolutely zero relationship about how fast or slow a reaction is and whether products or reactants are favored at equilibrium. They are not linked together in any way. Part of why I hate the fact that kinetics and equilibrium are taught together in Regents chemistry, because they're not the same thing. What species are included in the equilibrium expression? So the products of a reactants raised to their coefficients. You do not include solids or liquids. You do not put them into your equilibrium expression. Any solid or liquid, basically, that's in the reaction cross it off, do not put it in the products of a reactants go to products of a reactants raised to their coefficient. The reason why is that we only put in things that have concentrations. Solids and liquids don't really have concentrations because they're 100%. They're a pure substance. They're all the same thing. If you think about liquid water, it's all liquid water. It's not like 1 mole out of the entire liter is water. No. All of it is water. It's all water. So they don't have concentrations. They're 100% always. We do include solutions and gases because their concentrations can change, and you can absolutely talk about a solution having a certain molarity. How many moles per liter? Is it 0.1 mole per liter, 0.01 mole per liter? And gases have concentrations. You can increase the concentration of a gas very easily. When you think about the concentration of oxygen that's in any given room, you can change that. This is not saying that the solid or the liquid is not necessary for the reaction to take place. It absolutely is. You have to have that solid or liquid there for the actual reaction to go. If you don't have it there, it's not going to go. But you don't include it in the equilibrium expression. You simply negate it. You can put a 1 in its place and eliminate it that way. So, example writing in equilibrium expressions. We have this reaction, N2O4 goes to 2NO2, following our mold of products, which are on the right, divided by reactants, which are on the left, raised to their coefficient. We get a Kc expression for this. That's the concentration of NO squared divided by the concentration of N2O4. So again, notice that that 2, that's right there, got turned into the coefficient, got turned into the exponent for the NO2. Now, this is to make a point here. This reaction at 100 degrees Celsius, the Kc value is always 0.211. So it's saying that at equilibrium, we get a predictable ratio of products to reactants. It doesn't matter how much N2O4 or NO2 you started with. This reaction will always, when it's at equilibrium, its ratio will always be 0.211. Notice that in this case, K is less than 1. That indicates that at equilibrium, we're always going to have more N2O4 than we will NO2. It's saying that reactants will dominate for this reaction at equilibrium, larger denominator. Now, equilibrium constants and pressure. You can absolutely write an equilibrium expression, so that whole thing, K equals products of a reactants raised to their coefficient, with partial pressures rather than molarity. If you have a system of gases, just gases, then you can do the exact same thing. Now, in this case, instead of square brackets, because this is not molarity, if we have all gases and if we have partial pressures, then I can simply put in the partial pressure of the products raised to their coefficients divided by the partial pressure of the reactants raised to their coefficients, and it's going to work the exact same way. It's going to have the same setup, and it will have the same meaning. However, the value of Kc will not be the same number as that of Kp. This is called Kp now because we are dealing with partial pressures. So you want to kind of be careful if I ask you to write a Kp expression that you don't include square brackets. That's actually critical that you're telling me that I know that this is partial pressures and not molarity, because square brackets always means molarity. So there'll be the same relationship, meaning that Kp and Kc should predictably both be either greater than 1 or less than 1, but they won't be the same number. Weak acids. Weak acids with equilibrium. So we've seen this before. We've mentioned this many times. Weak acids only partly dissociate in solution. So we have this reaction of HA goes to H plus plus A minus. This is our acid dissociation reaction. Well, we can now write a K expression for this. Products over reactants raised to their coefficients, and now we call this Ka. So Ka for acid, and the Ka expression would be the concentration of the products, H plus times A minus, divided by the concentration of the reactant, Ha. And you can write any acid dissociation reaction and write the Ka expression for it. The larger the value for Ka, the stronger the acid. And I know that these are weak acids, but as I mentioned before in the acid-base unit, you can compare strength of weak acids, and we'll be doing a lot of that in this particular unit. So simply the larger your value for Ka, even if it's a weak acid, the stronger the weak acid is. If the Ka value is significantly greater than 1, that means that you have almost entirely products at equilibrium. So that's going to indicate that complete dissociation that the strong acid goes through. So if K value is enormous, then you know you have a strong acid and not a weak acid. Weak acids will have Ka values less than 1. You'll have more of the Ha rather than H plus and A minus. That 5% dissociation coming in. Weak bases and equilibrium. So base dissociation reaction that we've seen and already seen in practice writing before, right? The base plus water. Now remember, with the base dissociation reaction, you have to include the water. There's no way to get around that. You can include water, or you can leave out the water from the acid dissociation reaction, but you need it here because you need something for the base to take to accept the proton from. So that proton's being transferred from the water over to the B, and then you get Hb plus plus OH minus. Now the Kb expression, again, products over reactants raised to their coefficient, but we have a liquid. Liquids and solids do not get included in the equilibrium expression. So the Kb expression here is the concentration of Hb plus times the concentration of OH minus divided by the concentration of B. You still need H2O in the reaction, but you're not going to put it in the K expression. So this is an example of, yeah, you absolutely need that water in that reaction. We don't include it, though, because it doesn't really have a concentration in this expression of concentrations. Kb is called the base dissociation constant, again, B for base. And very, very similarly to acid, the larger the value of Kb, the stronger the weak base. It means that the more Hb plus and OH minus you're going to get, the more the base was able to steal a hydrogen from water. There's a big relationship between Ka and Kb. So if you consider an acid and its conjugate base. So this would be, for example, Ha versus A minus, right? That would be an acid and its conjugate base. Or to take an actual example, we could do, H2CO3 and HCO3 minus. Remember, acids and their conjugate bases don't react with one another. And hopefully you remember, the stronger an acid, the weaker its conjugate base. And we have this relationship. This is shown numerically here. The Ka for a weak acid and the Kb for its conjugate base. So this would be Ha and this would be A minus. When you multiply them together, you get Kw. This is the Kw for water. So this is 1 times 10 to the minus 14th at 25 degrees Celsius. They always have to equal the same number. So if Ka gets large, then Kb has to get small. So that's that thing that's saying if your weak acid is stronger, then its conjugate base is going to be weaker. Likewise, if the base gets stronger, if Kb gets larger, then Ka has to get smaller, because when you multiply them together, you always get the same number, Kw. So this is showing mathematically that this relationship that we talked about qualitatively in our acid-base unit. This is also why for our strong acids, their conjugate bases are so negligible because their Ka values are so enormous that their Kb values have to be absolutely tiny by comparison. And then the last thing about writing equilibrium expressions has to do with insoluble salts. Now, we've sort of been lying to you this entire time when you say insoluble and you say it doesn't dissolve. That's not actually true. Insoluble salts do dissolve. It's just that they dissolve very, very little, like on the order of 0.01 moles per liter. I think they're tiny, tiny, tiny amounts. They just can't dissolve. They're really, really garbage at dissolving, but they do dissolve a tiny, tiny bit. For example, barium sulfate dissociates a teensy little bit into barium ions and sulfate ions. Now, because the amount that it dissociates is so small, we do talk about it being equilibrium, that it's a reversible reaction, because the barium ion and the sulfate ion can absolutely come back together and create barium sulfate solid. Notice that I have a solid there. Well, I can write an equilibrium expression for this, absolutely, doing products over reactants raised to their coefficients. But this is a solid, so I'm not going to include it in the equilibrium expression. I need it in the chemical reaction because it's part of the balanced chemical equation, but I don't need to put it in the expression. This is now something called KSP. KSP stands for the solubility product constant. It's essentially the flavor of equilibrium that deals with insoluble salts. And I technically write this over the reactants, which are the barium sulfate, so you can sort of think of it as simply putting in a 1 in the place of the solid, that we don't include that solid or solids or liquids in the equilibrium expression. So we have this thing called KSP that has to do with the dissociation of insoluble salts. So they dissociate a little bit, but it is in equilibrium. Writing reactions. So you've written acid dissociation reactions and base dissociation reactions before. You'll be doing that in the first problem set for equilibrium again, but you'll also be writing KSP dissociation reactions. KSP dissociation reactions are actually fairly simple. All they are is the solid dissociating into its ions, and you can show the fact that it does it slightly by including a double arrow. So for example, write the dissociation reaction for magnesium hydroxide. So magnesium is Mg2+, hydroxide is OH-, so magnesium hydroxide is MgOH2. So the reaction would simply be magnesium hydroxide solid dissociates a little bit, that's our double-sided arrow, into magnesium ions and 2 hydroxide ions. Be very careful about this when you're writing these, because a lot of acid-base dissociation reactions, everything is a coefficient of 1. You know, HA goes to H plus plus A minus. It's a 1 to 1 to 1 ratio. With solids, it's not necessarily the case. We see that we get 2 hydroxides from 1 magnesium hydroxide. So just be careful about that, because in the equilibrium expression, if we were to write this, KSP, because it's a solid dissociating into ions, it would be the concentration of Mg2 plus products times the concentration of OH minus raised to their coefficient, right? So I need to incorporate that 2 there. And then I don't include the solid, so I'm basically done writing the KSP expression. I can put it over 1 sort of technically, but you don't include that solid in that expression. So just some practice writing equilibrium expressions. PbI2 goes to Pb2 plus 2I minus. This would be a KSP. Because we have a solid dissociating into ions, and I'm not going to include the solid in the expression, so products over reactants raised to their coefficient. So it's going to be the Pb2 plus times the I minus squared, and that's it. So I'm not including that solid. Then I have HF goes to H plus F minus. This is an acid, which I can clearly see, so this is going to be a Ka expression. So products H plus times F minus over reactants. I am including this. I'm including all aqueous and gaseous species. So Ka equals H plus times F minus over HF, all molarities. For the next reaction, 2SO3 aqueous goes to 2SO2 aqueous plus O2 aqueous. This is not an acid reaction. It's not a base dissociation reaction. It's not KSP. So sort of the fail-safe is just let's do KC for concentration. So I'm going to do the SO2 squared times the O2 raised to the first, all divided by the SO3 squared. Right, our coefficients become our exponents, and everything's multiplied together, not added. Then I have NH3 plus H2O liquid goes to NH4 plus OH minus. This is a base. This is a base dissociation reaction, so this is Kb. So I'm going to do NH4 plus products times each other times the concentration of the hydroxide. I'm not going to include the liquid, divided by the concentration of the NH3. So Kb expression, concentration of ammonium times the concentration of hydroxide divided by the concentration of ammonia, products of reactants raised to their coefficients. In the last one, I could really do this one of two ways. I could write a Kc expression, or I could also write a Kp expression. Notice I have all gases. Both are valid. If I simply ask for the equilibrium expression, you could give me Kc and you could use molarities, or you could give me Kp and you can use partial pressures. I'm going to use Kp and use partial pressures. So I'm going to do the partial pressure of the NO squared times the partial pressure of the chlorine gas divided by the partial pressure of the NOCl squared. And that's how we write equilibrium expressions. So tomorrow, or on Monday I should say, make sure you are ready to write some equilibrium expressions and understand what the magnitude of K is saying about the system.